This video is going to look at the so-called other trig functions and their graphs. These are the graphs of tangent, cotangent, secant, and cosecant. We're going to look at how they're related to sine and cosine and where the graphs come from or originate from. Then we're going to look at the characteristics of the parent function for each, such as the domain and range, the period, asymptotes, etc. Let's start with a review of right triangle trig and our old friend Secant. So for this right triangle here, I have an angle theta, the opposite side to it, the adjacent, and the hypotenuse opposite the right angle. The sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, tangent theta is opposite over adjacent, cotangent theta is adjacent over opposite, secant theta is hypotenuse over adjacent, and cosecant theta is hypotenuse over opposite. Now, how are we going to use this? Let's start with tangent theta. And from Secant, that tangent theta is opposite over adjacent. Now, using some algebra, I can say it's the same as opposite over hypotenuse over adjacent over hypotenuse. And the reason I can do that is because 1 over hypotenuse, 1 over h, over 1 over h equals 1. So I technically just multiplied by 1. And what that equals then, if you didn't catch it already, is that sine theta over cosine theta. And that's our first trig identity. Tangent theta equals sine theta over cosine theta. Now, because cotangent is just reciprocal of tangent, I also know that cotangent of theta is cosine theta divided by sine theta. And just using reciprocals again, I also know that secant theta is 1 over cosine theta, or 1 divided by cosine theta. And finally, cosecant theta is the reciprocal of sine, so it is 1 divided by sine theta. So the point of those trig identities was to help me develop the graph of tangent, cotangent, secant, and cosecant from what I know about the graphs of sine and cosine. So here we have the graphs of sine and cosine, and I'm going to use them to graph tangent. Because tangent is sine divided by cosine, everywhere cosine equals 0 is a problem. I'll be dividing by 0. I can't do that. So I'm going to have a vertical asymptote everywhere the denominator cosine equals 0. So I'll have one here at 3 pi over 2. I'll have one at pi over 2. I'll have one at negative pi over 2, as well as negative 3 pi over 2. The next thing I do to figure out the graph is look at where's sine of x is 0, because 0 divided by a number that's not 0 will give me 0. So anywhere the sine curve, the red line, crosses the x-axis, I will have a point 0. So I have a 0 at 2 pi, at pi, at 0, and at negative pi, and finally at negative 2 pi. Now, the last part's a little tricky to kind of fill this in, and I just need to really look closely. Remember, I'm dividing two things here. So let's look right here. Notice these patterns are going to repeat. I have a negative, very small number for cosine. Even more, let's start with here. I have a number very close to 1. Right? And I'm dividing by a negative, very small number. So a 1 divided by a very negative, very small is going to push me towards negative infinity. Similarly, if I have a value close to negative 1 for my sine, divided by a negative, very small, two negatives, that will give me a positive value. It's going to push me towards positive infinity, which now notice it's going to kind of fit our definition of asymptotes. And one more thing I can look at is where they're sort of equal, at least their absolute values are equal. So around here, or these are like all my multiples of pi over 4, or 45 degrees, where sine and cosine are the same, I'll have a positive over a negative, and that'll give me a negative 1. So I'm going to plot that point exactly. And similarly, I can plot positive 1 here, and this one's easier to see that they're equal to each other. Now I can just kind of sketch that curve. And that pattern's going to repeat, because I have the same thing going on. And there is my graph of tangent x. For y equals cotangent x, I'm going to have a similar case. Now I drew in the asymptotes because, the same thing, except I'm going to look where sine equals 0, and that's going to be my problem. And that's where I'll get the vertical asymptotes. So let's follow the same approach. Let's look at the points where they're equal. That will give me a negative over negative. The same value will give me a positive 1. Here's my 0. And then I'd have a negative 1. And looking a little closer, I see I have about approximately negative 1 divided by a negative very small number. That would go towards, or tend towards positive infinity. Similarly, I have a number close to 1 divided by a negative very small number. That's going to tend towards negative infinity. Now if you notice that, again, this pattern will repeat infinitely as well. I have all my zeros at the negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. And if I follow that pattern, I'm going to get a graph that looks something like this. And there's the graph of y equals cotangent x. For the graph of y equals secant x, all I really care about is the cosine curve. So I have that drawn in there. And so if I look at where does cosine x equal 1, well or negative 1, I can start with points there because I have 1 divided by that value. So 1 divided by negative 1 is negative 1. 1 divided by positive 1, do negative 1, positive, and I also have a positive over here. And what I want to do is just kind of look at that same reasoning I had before. I have 1 and I'm dividing by a number that's going to be between negative 1 and 1. So it's always going to increase in value. 1 divided by a number whose absolute value is less than 1 is always going to increase. So if I have 1 divided by a positive very small number, that's something that's going to tend towards positive infinity. If I have 1 divided by a negative very small number here and here, then something that's going to tend towards negative infinity. Positive infinity, negative infinity, and then I have 1 here towards positive infinity. And if I just sketch the shape, if you could always plug in more points if necessary, but the shape is the point of this, I'm going to get a curve that's going to look something like this. And again, that repeats infinitely. Notice it alternates between above the x-axis or below, but always greater than positive 1 or less than negative 1. And there's a graph of secant x. Following the example for secant x, I can graph y equals cosecant x. Plot, after I've developed the asymptotes, or the zeros of sine x, I'll plot the 1s and negative 1s. And following the same pattern, I'm going to get almost the same shape, just that it starts sort of, and has asymptotes in the different locations. It's almost parabolic, but if you plug more points in, it flattens out a little more than a true parabola. And there's the graph of y equals cosecant of x.